I am Dr. W. B. Gunule from Kamlanil Mahavidyalaya, Nagpur. Today we are going to discuss the factors which are affecting the stability of the complexes. And there are 7-8 factors are there, and that is nature of metallon, nature of ligand, role of pH, environmental factors, pH, solvent are the factors which are affecting, and important is the number of chelating, size of chelating. All these factors affecting the stability of the complexes. As we know that already we have seen the what is stability constant and stepwise stability constant, and after that the overall stability constant and their relation. And so in today's presentation we are discussing about the different factors which are affecting the stability of the complexes. So the today's topic is the factors which are affecting the stability of the complexes, and there are total 7-8 factors are there which are affecting the stability of the complex. And here what are the different factors affecting the stability of the complex are shown. First is the nature of metallon, nature of ligand, role of solvent, Chelate effect, environmental factor, concentration, and role of pH. As we know that stability constant vary with the wide range of values, and we can consider the reaction of particular metal with the number of ligand, and they show the speed of the reaction, and these rate of this reaction or the formation of this complex can be affected by a number of factors, and it is not possible to conclude that particular ligand or particular metal form complexes of high or low stability. No single factor is expected to account for the stability of the coordination compound. They are affected by many physical and chemical factors, and these are the some important factors which are affecting the stability of the formation of complex. So first factor is the nature of metallon, and in case of nature of metallon, there are three parts are there. First part is the charge on the central metallon, second is the size of metallon, and third is the electronegativity or the charge distribution of the metallon. So in case of the charge on the central metallon, and it is observed that stability constant vary, and in case of the charge on the metallon, and the stability constant for the complex increases with the charge on the central metallon. So the stability constant affecting the value of stability constant, and here stability constant for the complex increases with the charge on the central metallon. Metallon having high charge density from the stable complexes forms stable complex. Charge density means ratio of charge to radius of the ion, and smaller the size of and larger the charge on the metallon, more stable are the complexes. This is because smaller, more highly charged ion allow closer and faster approach of the ligand, and greater force of attraction result into the stable complex. And hence we can say that when a metal ion form complexes with same ligand in more than one oxidation state, the complexes of the higher oxidation state are always more stable than those of the lower oxidation state. In general, we can say that greater the charge on the central metallon, greater is the stability of the complex. So remember that greater the charge on the central metallon, greater is the stability of the complex. So we can say that stability of the complex depends upon the charge on the central metallon in the complex. For example, complex of Fe3 plus ion is more stable than the complex of Fe2 plus, because Fe3 plus have the charge, Fe have 3 plus charge. So here are the two complexes are shown. In this complex hexacyanoferrate, ferrate. So in this case Fe having 3 plus charge, here Fe having 2 plus charge, but this is greater, more stable than the second. So Fe complex of Fe3 plus are more stable because having greater charge. So charge of central metallon are affecting the value of stability constant. So this is one example, and second is the size of metallon also affecting the stability constant. The second part of the nature of metallon is the as the size of metallon decreases, stability of the complex increases. So smaller the size of the metallon, greater the stability of that complex. So if we consider bivalent metallon, then the stability of their complexes increases. with the decrease in the ionic radius of the central metal ion. And here one example is given, and manganese, iron, cobalt, nickel, copper, zinc, first transition stage element, all other 2 plus, but the having a positive charge, and ionic radius, see the radius decreases in this way. So as the decrease of ionic radius or the size, we can say that there is an increase in value of the stability constant. So therefore we can say, from this we can say that the order of stability is Mn2 plus is less stable than Fe2 plus, which is less stable than CO2 plus, which is less stable than Ni2 plus, which is less stable than Cu2 plus, and which is less stable than zinc 2 plus. So zinc 2 plus having greater stability as compared to copper, and copper have greater than nickel, like that. So this is the order in this case. So these are the two important, A, B, and another third point is also there, that is the charge distribution of metal ion. So in this case, this is another factor determining the stability of the complex. In case of nature of metal ion, we classify the metal ion into two types, and generally there are two types of metal, class A metal and class B metal. So what is class A metal? Shown here, F minus, Cl minus, Br minus, I minus. So here are shown in this slide what are the class A, example of class A metal, and these are the example of class B metal. And what is class A? We can say that these are electropositive metal and include the alkali metal, alkaline earth metal, most of the non-transition metal, and those transition metal having only few d valence electron, like scandium, titanium, vanadium, and such metals have relatively few electrons beyond an inert gas core. And class B metals include less electron positive metals and heavy metals such as rhodium, palladium, silver, iridium, platinum, gold, like that. From this category, this is the second category. These have relatively larger number of d electron beyond the inert gas core. So class A metals and class B metals. So class A metals which attract electron weakly from the most stable complex with those ligand slightly electron negative atoms such as nitrogen, oxygen, fluorine. Whereas in case of class B metal, class B metals from the most stable complexes with pi acceptor ligand containing phosphorus, sulfur, arsenic, bromine, iodine. Therefore the ion with the higher electronegativity give more stable complex. So ion with the higher electronegativity give more stable complex. So this is another part. So these are the three parts are there: charge of metal ion, size of metal ion, and the charge distribution of metal ion are affecting the stability of the complexes. And second important factor is the nature of ligand. As we know, what is the ligand? Ligand is the group attached to the central metal ion in the complex. And these nature, there are different types of ligand, and depending upon the size and charge of ligand, dipole moment of ligand, basic character of ligand, because ligand show basic character because they are lone pair, they donated, so it has a Lewis base. So all these three factors, size and charge, dipole moment, and the basic character of ligand affecting the value of stability constant of the complexes. And in case of the nature of ligand, these are the 3 point ABC, and the first is the size and charge of ligand. In this case we can say that in general small ligand with higher negative charge form stable complex. So depending upon the size and charge, we can say that small ligand with a higher negative charge form the stable complexes. For example, F minus, small size, highly negative, forms more stable complex with Fe3 plus as compared to chloride ion, bromide, or iodide. Therefore, small fluoride ion forms more stable complex with the Fe3 plus than the large Cl minus ion. This is due to the easy approach of ligand towards the metal ion. So this is the one point, that size and charge affecting the stability. B is the dipole moment of ligand. Dipole moment is the is having positive and negative poles, and in that case for neutral ligand, larger is the magnitude of permanent dipole moment, greater is the stability of the complex. For example, order of stability of the complex formed by some neutral ligand as given: ammonia is greater than ethylamine, then which is greater than diethylamine, which is greater than triethylamine. So this is the order in case of the dipole moment. Third important factor is here also now, basic character of ligand. As we know, metal ligand bond involves donation of electron pair from ligand to the empty orbital of central metal ion, and therefore we can say that here, greater the basicity of ligand, greater will be the tendency to donate the electron pair, and this means that most basic ligand will form more stable complex. We can generalize that strong bases perform strongly as ligand too. And for example here, so as we know, ligands have tendency to donate electron pair and therefore act as and showing the basic character. So therefore greater is the tendency to donate electron pair. This means that we can say that more basic ligand will form more stable complex. And example here we can give Cn minus and ammonia molecule, cyanide and the ammonia, which are strong bases, are also good ligand and form many stable complexes. Ammonia should be better ligand than water. Such type of behavior is observed for the class A metal, that is alkali metal, alkaline earth metal, lanthanide, actinide. However, it is not true for the complexes of the metal type B, where other factors like back bonding are also play an important role in that case. So this is the second nature of ligand, and in case of nature of ligand, three important points are there: size, charge of ligand, dipole moment, and basic character of ligand. And third important point of the third important factor is the role of solvent. Sometimes solvent also affecting the stability, and as a complex formation involve the formation of covalent bond, solvent with low dielectric constant and low dipole moment are expected to increase the stability and the stability constant of the complex, and therefore potential stability constant value increases with the decreasing dielectric constant and dipole moment of the solvent, and therefore we can say that strongly donor solvent decreases the stability constant of the metal complexes. So role of solvent is also very important in the formation and of complex and about the stability of that complex. Fourth important point is very important from the stability of the complex, and the stability of the chelate depends upon the factor. Two important factors are there. One is the size of chelate ring, number of chelate ring. So in case of size of chelate ring, one factor which is very important in the chelation is the size of the chelate ring. And as we know, what is chelate? Chelate is the ring formation in the complex. All chelates are complex, but all complexes are not chelates. So therefore, when the complex is formed, the ligand should form the ring with the metal ion. When it form the coordinate bond, formation of ring is take place. So chelate is obtained from the chela and means formation of ring. So there are multidentate ligand from the chelate complexes, and one factor this is important in the chelation is the size of the ring of the chelate ring. It has been observed that metal chelate having 5-membered ring are more stable. Chelate having 6-membered ring, ligands such as ethylene-diamine, oxalate ion, glycine, dimethyl glyoxime forms quite stable 5-membered chelate. It is also noted that only the 5-membered chelates are more stable than 6-membered chelate, where atoms in the rings are joined only by a single bond. However, 6-membered chelate having double bonds or unsaturation in the ring are more stable than the corresponding 5-member chelate rings. So formation of ring, generally chelates are more stable than the simple complex, but again now chelates are more stable because stability is there in case of the complex. Second point here, number of chelate ring. As we in general that increases the number of chelate ring, increases the stability of the complex. So greater the number of chelate ring, greater is the stability. Another factor that is in the chelation is the number of chelate ring. It has been observed that increase in number of rings within the chelate result a greater stability. It is also found that formation of rings around the metal tends to provide greater stability than the formation of single ring. For example, here is shown chelate structure is one is shown in the slide having 3 fused ring system is much more stable as compared to the chelate 2 involving 2 rings. So in this case there are 3 rings, in this case there are 2 rings. So here other 2 rings are here, but here 1, 2 and 3 rings are there. So this is more stable. This is 1, this is 2, this is 3. Here only 2. This is 1 and this is 2. So only 2 rings are there, in the first one, and therefore this is more stable first complex and as compared to second. Another example is given here, how the nickel form with the complex with the ammonia, and here nickel form the complex with the ethylene diamine. En means ethylene diamine and form Ag. So this is more stable. So the value of the stability constant is shown, log beta equals to 7.79, log beta equal to 18.1. So this is greater value of the stability constant is there, and therefore multidentate or the chelate, this complex from the chelate ethylene diamine. In this case, this is monodentate. Monodentate ligand do not form the chelate, but ethylene diamine form the chelate. So this is chelate, this is simple complex. So chelate have greater stability constant. So we can say that size of chelating and number of chelating affecting the stability constant of the complex. And number 5 factor is the that is the environmental factor. And in case of environmental factor, we can say that that is temperature and pressure. It includes the temperature and pressure effect. The complex containing volatile groups like water, ammonia, ethylene diamine in the coordination sphere are always less stable at elevated temperature and generally decompose when heated. And one reaction is shown here. This reaction. So fifth factor is the environmental factor, and it includes temperature and pressure effect. The complex containing volatile groups like water, ammonia, ethylene diamine in the coordination sphere are always less stable at elevated temperature and generally decompose when heated. For example is given here, chromium, this complex reaction is given. This is a triethylene diamine chromium chloride complex. At this temperature they form this type of complex, and in this case similarly there is a reduction of pressure in the compound generally leads to the loss of volatile component, and therefore it affects the stability of the complex compound. So this is another factor, that temperature and pressure also affect the stability constant of the complex. And number 6 is the concentration. We can say that the stability and even existence of complex ion in the solution are affected by the concentration changes. Solid complexes have greater affinity for the metal ion as compared to the group of coordinated. For example, yellowish solid copper chloride ion dissolved in water to produce pale blue solution containing copper H2O N2 plus complex, which on adding excess of chloride ion given a green solution. So this concentration is the another factor which affecting the stability of the complex. Number 7 factor is the role of pH. It is also observed that complex of the metal ion by the ligand increases with the increasing pH. This is because in aqueous solution metal ion and the H plus ion are form the common ligands, that is in presence of excess of H plus ion the ligand tends to form proton ligand complex in preference to metal ligand complex. So pH is also very important for the formation of complex. And last factor is the steric hindrance, and as we know steric hindrance means if the more number of ligand accommodated in the coordination sphere, then the stability decreases. One of the important factor of significance in the chelation is the steric factor. This is associated with the presence of bulky group either attached to the donor atom or near enough to it to cause mutual repulsion steric effect between the ligand, which result in the weakening of the metal to ligand bond. Therefore, substituted ligand containing large bulky groups form less stable complex as compared to the unsubstituted smaller ligand, and this reduces the stability of the chelate. Example is given here. This is the one example of simple ethylene diamine form the most stable complex as compared to substituted. Here the 2 hydrogen is substituted by methyl group, here 2 hydrogen replaced by the methyl group, and this is the substituted group. So this is stable and this is unstable. So bulky groups are present, then it is unstable and as compared to the unsubstituted groups. As we know that a number of ligand if enter in the coordination sphere one by one, so the bulky groups forms and therefore stability decreases. So depending upon the steric hindrance, whether the ligands are bulky or substituted or substituted, depending upon that they are affecting the value of stability constant. So these are the 7-8 factors which are affecting the value of stability constant of the complexes. So today we have discussed the different factors which are affecting the stability of the complexes. that is nature of Metallon, nature of ligand, role of solvent, pH, and important is the number of chelating, size of chelating. All these factors affecting the stability of the complexes.